title is Secure Parallel Computation on National Scale Volumes of Data by Sahar Mazloum, Fiyong Lee, Samuel Manalucci, and Dov Gordon. And Sahar will give the talk. Over to you.
Hi. Hi, everyone. Thanks to organizers for organizing such a great event. Thanks for all your efforts and time. So I'm glad to be here today. My name is Sahar Mazloum from George Mason University. In my talk, I'm going to show you how we can learn on larger scale data with security and privacy. And as you mentioned, it is the joint work with my colleagues, Fihong Samuel, and my PhD advisor, Dov Gordon. So first, let's see what is the problem. Every day, we generate huge amounts of data, which are mostly sensitive, such as medical or financial records. And service providers like these companies, they look at our data and clear to run some machine learning algorithm on them. But at the same time, they put our data at the risk of data breach because they wanted to provide some services for us, such as movie recommendations or targeted advertisements. One of the promising ways to protect our data that has been around since World War II is using cryptography. But it is interesting to know that out of almost 14 billion records in the internet that has been lost due to data breaches since 2013, only 4% of them have been encrypted and almost useless to the attackers. So I guess one of the main reasons that make this prohibitive, using cryptography is that computing unencrypted data is challenging, and sometimes the cost is very expensive that many companies still refuse to adapt and use it. So as this workshop is about, secure computation is actually an appealing solution and makes it possible for multiple parties to jointly compute function under secret data without leaking any information about the party's input. So this computation and this function can be a machine learning algorithm, right? So in my talk, I would like to focus on, for example, a machine learning algorithm called matrix factorization that has been extensively used by companies, as I mentioned earlier, for recommendation systems and advertisements. So in matrix factorization, the goal is to decompose a matrix of ratings into two matrices of users and items. And the model is trained using gradient descent method, which is a very popular optimization algorithm, has been used in many machine learning computations, such as deep learning, super vector machine, and so on. So here, the model using gradient descent method is updated iteratively until a local minima is reached. And here, I'm just showing the more detail of like how the gradient descent can be applied on matrix factorization problem. So imagine the rating matrix of the, for example, movies consists of rating values given by users to different movies. So to decompose the matrix R into matrices U and V, we should minimize that objective function down there by computing and updating gradient values of users and movies in each iteration of training and learning process. So what we did, we looked into machine learning community to see how they do this type of computations faster. And we learned that there are some frameworks that they use to make it faster, and they are using basically parallel computation. And the idea is that if you can model your problem as a graph, so for example here, we model this matrix factorization problem for movie recommendation systems as a bipartite graph, which the left nodes are users and the right nodes are movies, and the edges showing which user ranked which movie, and it contains some weights that is carrying the rating values. So the idea is that if we can model our problem as a graph, if we can solve it using the frameworks, basically the main problem is solved. And the framework consists of three main operations. So basically they say any computation you want to apply in this graph, you can break it down into three main operations. And they call it gas model of operation. So the first operation, so first they assume that the data is reside into a graph structure, and the result of computation can be reached through an iterative process in which at the first step, the data is gathered from the edges to the neighboring nodes. We call this process gather. The second phase, they apply a simple computation on the data at the node. In here, we have this computing of gradient descent values. And in the final step, they just scatter back and update the edges with those like new values for movies or users' profiles. So that's how they conduct this graph computation in parallel, and parallelize the computation. So there has been a work done by Naik et al. To perform the secure version of this graph parallel computation, which is called GraphC. And one of the challenges that they had was basically imagine everything is here either encrypted or secret shared or some way the data is the graph is data oblivious. But when the computation is going to happen, when we are doing gather and scatter operations, we are revealing the edge structure. So in their work, instead of, for example, using ORAM to hide the access pattern here, they use their own customized and tailored solution, and they used an oblivious sort to hide node degree and edge structure of the graph. And this operation is quite expensive, and complexity of that is equal to E plus V, log S square E plus V, in which E is the number of edges and V are the number of vertices. And they applied their framework on a data set of 6,000 users, 4,000 movies, and with 1 million ratings, and they did it in almost 13 hours. And the threat model was semi-honest. Basically, none of the parties could act maliciously. So in our previous work that was done like in CCS 2018, we asked this first question, we were the first to ask this question that can we create faster secure computation algorithms and allow the attacker to learn some leakage. And then we later provide and proof and formal bound on the amount of data that is learned by the attacker. And we prove that it is differentially private. So because of that, we explored this idea of relaxing the security notion in secure computation by allowing some leakage that preserve differential privacy. And then we designed our graph parallel computation framework, we call it Obliv graph, in which basically in order to hide the node degree and the access structure of in the graph, we used dummy edges. We basically shuffled and mixed dummy edges into the real ones. And the number of dummy elements that we added in this graph was determined and dependent on the differential privacy parameters, epsilon and delta, in which I will talk about it in the experiments, and I'll show which parameters we chose. So because of this relaxation, so we were able to remove that oblivious sort, which was expensive, and replace it with a cheaper solution, oblivious shuffle. And I'll show you how much improvements we could achieve. So for example, imagine we have users submitted their input, either secret shared or encrypted, send it to the servers. And we assume that they are untrusted, non-colluding servers. One could belong to Amazon, the other could belong to like Google, for example. And what they do, basically, in order to perform a secure computation, like matrix factorization, we designed a secure version of all of those steps, as I mentioned, like gather, apply, and scatter. So we came up with a new oblivious version of those, along with the oblivious shuffle that we introduced earlier. So then we were able to shave off another log factor, from this complexity, and we brought it down the computation time from 13 hours to 2 hours. And note that the threat model is still the same. This is a semi-honest model. But then, as you can imagine, we asked the same question again, that can we do better? We looked into like several recent results in secure computation and realized that there are some works that minimize the communication costs by restricting the number of computing servers to 2 or 3, assuming an honest majority of the servers. And when representing the computation as an arithmetic circuit over a ring, as we do here, the cheapest of these results by Gordon et al. Requires sending only 1.5 ring elements per party per circuit gate. So by leveraging the result of low communication MPC and the previous work that I described, the Obliv graph, which was a security relaxation that allows the computation servers to learn some differentially private leakage about inputs, we were able to construct an MPC protocol and we improved the same computation results with same setting, like 6,000 users, 4,000 movies, and we brought down the computation to 25 seconds. And also, it was not only limited to small matrices and a small data set, we were able to expand it to larger data sets. For example, we could do matrix factorization on the largest data set that is Lens providing, which is 20 million ratings. We could do it in less than 6 minutes. And we also computed this histogram or counting problem, which is like a canonical example that, for example, census data is how it's gathered. Like we wanted to see how many users are in a zip code. We ran it on almost 300 million users, and we could do it in less than 4 minutes. But the thing is, we actually, as I mentioned, we were inspired by this Gordon et al. Work that they were providing low communication MPC, and we increased the number of servers that we had from 2 parties into 4 parties. So by that, we could just achieve following results. So basically, we could replace that expensive quasi-linear oblivious shuffle with just a linear oblivious shuffle. We could tolerate at most 1 malicious adversary. And also we could replace that Boolean circuit with fixed point arithmetic computation. But the thing is, merging these constructions together is not like plug and play, and it has its own challenges that we wanted to merge them, and became some difficulties for us. So for example, the one that I'm going to talk about is related to this graph parallel computation. So basically the idea is that we don't want the parties that are accessing the data, basically reading the content of like reconstructing the idea of the vertices. We don't want them to know the shuffling and permutation pattern, because then they know everything, right? So because of that, the solution that we had was we partitioned the task between 2 groups of the users. So we let one group do the access to the data, the other group does the shuffling, and they don't know about each other's operations. And I will actually show it to you in the overview graph. But second challenge that we had, for example, because we wanted to support a malicious adversary, we had to verify the result of each operation to detect cheating behavior. So because of that, we had to implement authentication on ring elements. And we used, for example, this extension ring idea from SpeedCTK paper. So if I want to show you like an overview of the idea of like how these 4 parties can work together, we have like one set of parties, Alice and Bob. The other set are called Charlotte and David. Basically, I wanted to just fill this gender gap. So I have 2 females and 2 males here. So as a first step, I asked like Charlotte and David do the oblivious shuffle, and the other set of parties verify that operation, that there is no cheating behavior detected. Then they do, this group of Alice and Bob does the oblivious gather, which access the data. The other group verifies the operation, and so on. So basically, in the oblivious apply, both set of parties, they compute a functionality, which in this case could be computing gradient descent values in matrix factorization algorithm. And the 4 party all together, they do the cross-check validation. And at the end, the set of parties that were responsible to access the data, Alice and Bob, they could scatter back the data to the edges, and Charlotte and David, they just verify their operation. So basically, in any of these steps, if any of these parties cheat, so basically the rest of the parties would abort. So with this construction, we could improve the communication cost by 230 times in oblivious shuffle and almost 880 times in oblivious apply. And the kind of like one of the interesting challenges that we had was we wanted to do fixed point arithmetic computation, but we had to deal with truncation problem because we wanted to handle multiplication. And as you saw, we have like, we wanted to like minimize that optimization algorithm in the gradient descent computation. So we had to handle this truncation, and as a result of that, we could have some rounding errors that we had to handle that as well. So the protocol of Gordon itself passes through a dual execution of mask circuit evaluation. So imagine each group is doing some computation locally under masked values. And to ensure nobody has cheated in the execution, they have to compare the result together. And if those results doesn't match, so they abort, right? So it's a cross-check validation step. But in our computation, since we are computing like gradient descent, algorithm, we are dealing with decimal numbers, and in some occasions their computation might be different in different sets of computations in different like groups. So as a result of that, this operation might fail, and this comparison might fail, but it doesn't mean that there is a malicious behavior or cheating behavior. It's because of the surrounding error and computation error. So in our work, we showed how to handle rounding error securely, and which allowing us to leverage the efficiency of this protocol for fixed point computation. So let me show you what I mean by requirements for the truncation. So because addition, we are going to support addition and multiplication. So addition is kind of like easy. It can be performed locally. The challenge is doing multiplication with truncation. So for example, we have x and y, which are fixed point numbers with d bits for the fraction part. So the result of the multiplication is a number that has its own, that has at least 2d significant bits in the fractional portion. So truncation is needed to throw away the d least significant bits and note that the output of multiplication is the mass value of the truncation of x and y. It's not the x and y itself, it is the mass value. So imagine if we wanted to do truncation on the mass value, it would be kind of like more challenging. So to solve this problem, we provide a method to handle this truncation for our four-party mask evaluation. And it is actually a nice technique because it doesn't have any additional overhead. So we achieve the same overhead. We could achieve this error correction without having extra overhead. So just to give you a summary of like the results and our setup like for experiments. So we ran these experiments on AWS and also on our LAN network inside of the lab. These are the set of parameters that we applied. For example, we use epsilon to be 0.3 and the delta to be always 2 to the negative 40. And we ran it on different data set size. And here, as I mentioned earlier, so the state of the art was doing the computation of matrix factorization on movie lens dataset in 13 hours. And the initial work, we brought it down to 2 hours. And the recent one that basically I just described, we brought it down to 25 seconds. And with more, we made some improvements and optimized the implementation by using like ASN chip and other optimizations to the code. So basically, the running time would be even less than 25 seconds now. And also, this chart shows this for larger data sets, like for example, for 10 million and 20 million ratings of matrices. So in these two graphs, in the left side, we are showing the effect of differential privacy parameters epsilon and delta on runtime in matrix factorization graph with size 1 million edges. And in the right, we just break down this running time to different phases of this operation to see which one is more expensive and which one took extra time to run. So as a summary of this work, our goal was trying to show that we can learn our larger scale data sets with security and privacy. So what we did, we basically tried to have like design this privacy preserving machine learning algorithm, and we leverage differential privacy to relax the security notion and to improve the efficiency. And we use this 4-server model with at most 1 malicious corruption. So with that, I end my talk. Thanks for your attention. So the work was accepted in Usenix Security 2020. The link to the Git repo is in the paper available, and the security proofs will be and the ePrint will be up soon. Thanks.
Okay. Thank you. Okay. If anybody has questions, they're invited to write them on the questions and answer sections. I don't see anything at the moment.
Hello.
Hello.
Yeah, I have a question, Sahar.
Yes.
Thanks a lot for the nice talk. I just want to ask very briefly. So you use the protocol by Gordon et al., but I wonder if you also consider this protocol called Trident by Rahul and Ajit in Usenix 2020, I think.
No.
It's also 4 parties, and it also allows you to like only 3 parties need to be online in the online phase, so that may be good for your application.
I guess it would be actually. We haven't had a chance to look at this paper as you mentioned, if it accepted recently, because this work has been accepted like a while back. It is a Usenet security 2020, but it was accepted a while back. But if actually, would be glad if you can share the name or the paper with me, it would be great. I'm looking forward to read it.
Okay, amazing. Thank you.
Thank you.
Yes. Anything else? No. So I had one question. It occurs to me. So when you do this setup where you have two pairs of servers that do the computation, so one pair of servers do something, the other pair of servers check what the other two guys did. So and this is secure against one malicious server. Would it also be secure if in the other pair there was one passive corruption?
I guess not, because our security model, the threat model, was at most one malicious adversary. You cannot, if there is a cheating behavior in the other set of parties, so basically we have one.
Sorry. So what I meant was that if in the other pair there was one semi-honest corruption.
I guess that would be a problem again, because the goal is, I have to think about, the goal is, I guess, here that none of the set of two parties, they know, the parties that access the data know the shuffling pattern. So if one of the set of parties having a cheating behavior, like malicious behavior, so, I have to like.
No, I see. So it would only work if the guy who corrupted this guy semi-honestly was not working with the other guy who was malicious, actually. Then it would be fine, but otherwise, of course not. Okay, great. I don't see any other questions on the Q&A session. So maybe we should go on.